right, everyone. Hello. Welcome. And thank you for coming. So if I could have your attention, we'll run through a few reminders and announcements for what's happening this week and see if you have any questions. Thank you. So the practice homework that's out there, it is just practice. It's been posted since Thursday, just 3 questions, very short. Try them out if you wish, and they will be submitted, your answers automatically on Wednesday, tomorrow night at 11 o'clock. The GSIs then will be getting those as long as you've designated who your GSI is, which you need to do too at that tool site. And then they're going to get the practice at grading and seeing how that works, because a few of them are using this for the first time too. Those solutions to those questions will be available right away after the submission time tomorrow night. And on Sunday by midnight is when we say they have to have all their grading done so that the grades or scores can be released back to you. So that's how it will work every week. So the first real homework goes up on Thursday morning before we meet again. And that one is going to be submitted Wednesday the 26th. It's again a week to do it. Longer questions there. I think there's 10 total instead of only 3. But it is on the material that we have wrapped up already. So once it goes up on Thursday, you can try all the questions out. It is up through chapter 4 that we finished last Thursday, not on the probability that we're starting today. That homework will count for points. There will be about 10 or 11 homeworks during the semester. We will drop the one lowest score. So again, if you are still trying to get in the class, there's about 20 some still on the wait list and don't quite get that first one done, you could have that one be dropped. No labs meeting today or tomorrow since there were no labs yesterday. Next week's lab will be module number 2. Bring that to work on and look at pre-lab 2 sometime and work through that short assignment before your labs next week. I had some students panicking that they didn't know where to turn in that pre-lab assignment because they thought it was due this week. It's due next week before your second lab. All right, office hours have started. You may come over to any of those that are posted. And those are the primary announcements that I have. Do you have a question or comment at all before we turn to our material? Yes? C-Tools has the filled-in notes, if you missed any over the first few weeks, up through Chapter 4. The Chapter 7 that we start this week, any part I cover this week will be posted by the end of the week. So every Friday they go up, so I know how much was covered during that week. And then after drop-add deadline next week, instead of putting them up on C-Tools, I will have them available in the office hour room, a couple binders with those notes there. And we are capturing the Tuesday, Thursday section of notes, of presentations. So I hope to put those up and get that going later this week. We finally got everything to work for audio and capturing things correctly. So we should be able to see your Tuesday, Thursday notes and interactions available through iTunes U starting this week. Any other questions or comments? Questions or comments? All right, I do have one clicker question today. It's regarding the scores on that practice quiz that we had last week. So I have a histogram of those scores, and we'll see if you can comment on the relationship between the mean and the median based on what the histogram looks like. So I'm not seeing my little iClicker thing coming up, but let me see if this allows you to start polling. Are you able to vote on, based on this histogram of scores, 5 points maximum? What do you think about the mean in terms of what it would be expected to be relative to the median? Is it allowing you to vote? Yes, okay. I'm not able to see it here, but I can see it here. This is based on Chapter 2 ideas. I think you need to talk to your neighbor and see which one, A or B, should be the answer. We've got A and we've got B as the primary possibilities. See if you can convince your neighbor that your answer is right. Mean and median. All right, let's call it All right, you're convincing your neighbor to go with B. What kind of shape do we have here? It is skewed, definitely. Skewed in which direction? Left. Fairly prominent skew to left. Which measure is more affected by skewness or outliers, the mean or the median? The mean. And it gets affected by being pulled towards that direction of skewness or towards those outliers. If you throw in a couple of small values, and most of them are large, those small values get averaged in too and start to bring the median, or the mean, that is, down towards the left. So the mean is the one that is expected here to be smaller. B was the correct answer. Smaller than the median, slightly smaller. Now, not drastically so here. It's only a scale of 1 to 5 for the most part, but it is slightly smaller. The average got pulled down slightly compared to the median. Most, though, getting 5 out of 5. Those 5 questions that we polled last Thursday are up on C-Tools. They're without the solutions, and then the last slide is the solution. So if you want to look at them again or go through them again, you may for any kind of review. All right. So the mean is affected by outliers. The standard deviation is affected by outliers or skewness. We talked through some of those different measures of center and spread and which ones you'd prefer to use in which kind of situations. Here I would prefer to report the median or maybe the 5-number summary, so the quartiles would be provided too. All right, we have moved from chapters 2, 3, and 4, how to summarize data with graphs and numbers, how you collect that data in useful ways so you can use it for inference in sampling and experimental design or observational studies, chapters 3 and 4. We turn now to chapter 7, probability. Chapter 7, probability, we're skipping 5 and 6. Those will come later when we do that material with the inference part of it, which are some later chapters in the text. So we combine them with that material later. So we're moving on to probability. I have a fair die, right? What are the possible outcomes of a fair die? What are they? 1 through 6. Before you roll the die, do you know which one will occur? No. That's why it's a random experiment, a random phenomena. What would you assign to be the probability of getting a 4? 1/6. Probability, big capital P. Probability of any kind of a random event or outcome. In this case, getting a 4. Let me fix that. Getting a 4 is going to be 1/6. So the probability of getting a 4, you say it's 1/6. Why do you say it's 1/6? Because there are 6 outcomes? Is that the only reason? Aren't there possibilities where those 6 outcomes may not be equally likely? Here they are, if it's a fair die, so 1/6 does work that way. If you have a certain number of outcomes, they're all equally likely. The probability is 1 over the number of outcomes. So if I were to roll the die a few times, and I haven't seen a 4, am I more likely to get a 4 on that next roll because it should come out 1 out of 6 times? No. It's not in the short run, it's in the long run. If I were to roll the die a large number of times, in the long run I'd expect that fraction of 4s to start to get closer and closer to 1/6. That's what we assign as the probability. We can think of probability in a couple different ways. We can think of probability in terms of a subjective probability or a personal probability. This is more for events that don't necessarily end up being able to be repeated. And it's what you think. It's a degree to which you believe a certain outcome will happen. They should still follow probability rules of being between 0 and 1 and things like that. But we're going to focus on these other 2 definitions or ideas of probability. Both of them have to do with being a proportion. So I really want to think of probability as a proportion. And one way to view that is to think of probability of some event as being the proportion of times it would occur if you repeated it over and over and over, many times. Not in the short run, but in the long run. The proportion of times you'd see a 4 if you rolled the die many, many, many times. Or you can think of it more with our basket model. The basket model was that model that we thought of as being, here's our population of interest, and there's a lot of balls in that basket. Those items in that basket have different characteristics, and we're trying to learn about those characteristics. In this case, our population of balls are blue or white. There are 3 blue and 7 white. So if I were to select a random sample of just 1 ball from that basket, what would you assign to be the probability of seeing a blue? 3 out of 10, 3/10. So if I pull that ball out of the basket, is it going to be 3/10 blue and 7/10 white? That ball is going to be either blue or white. After you look at the ball that you pull, there's really no more probability because it either is blue or white. If I pulled out a ball, look at it, it's blue, and say, what's the probability of getting a blue? You'd say, well, 1, it is blue. There really is no probability anymore. That's somewhat like that confidence interval idea we talked a little bit about last week, where every interval that's made either has the true proportion in it or not. After you look at the interval, it's either correct or not correct. But you hope it's going to be correct because it was using a method that gives you a blue ball 30% of the time, or a correct interval 95% of the time. So here it is, the proportion of balls in the basket that have that attribute. If you were to go to a doctor's office and talk through your symptoms, and the doctor says, well, there's a 70% chance you have this disease. You don't have 70% of the disease in your body, or your body's not with that disease 70% or anything like that. You either have the disease or you don't. But if you looked at similarly situated people with your conditions and symptoms in a population, about 70% of them would have the disease based on the model behind that. So the probabilities that we talk about are statements not about individual outcomes. When you pull out a value from that basket, it either is blue or it's not blue. It's not about individual outcomes, but rather it is a statement about the basket, the population. We can talk about probability before you look at the outcome, but not after you look. And we'll talk about that a few more times along the way. So in your chapter 7, we're going to focus on sections 1 through 4. You do not need to read 5, 6, and 7, those last 3 sections. A little more advanced probability there. The book goes through a lot of formulas with this big capital P notation and lots of A's and B's for events. What we're going to do is really do all of those formulas today, but we're going to just do them with an actual example, and without even thinking too much, we're doing the formula correctly. Then we'll look at the formulas and see, oh yeah, we did do it that way, and understand that we can handle any probability question that comes our way. For that, we're going to take a look at this one two-way table of outcomes on page 34. Made it a nice example. It's out of 1,000 customers. Did some online shopping and asked them whether or not they received the items they ordered on time. And then generally, are they satisfied with their experience or not? Sometimes if you order online, you get those pop-ups. We'd like to ask you a survey since you've been going to our site and getting your feedback. So here's a table that describes these 2 variables, satisfaction level, satisfied or not, and on-time status. Did you receive it on time or not? Both categorical variables. One of them, the outcome of interest, might be the satisfaction, and does it depend on, or is it related to the explanatory variable of on-time status? So here are our data. We have 1,000 customers. Someone tell me what this 800 right here represents, that count. That's telling me what about this background here? There were 800 customers who were satisfied and did receive their items on time. And then there was another 100 customers who were not satisfied and didn't receive it on time, and so on. How about the 820 right here? That's the total number of customers that are satisfied. So we're going to think of probability as proportion and answer a few probability questions. I simply have to find proportions. The first one is, if I were to randomly pick a customer, what's the chance that they are a satisfied customer? They were satisfied with the experience. So I need the proportion. What proportion were satisfied? 820 was our total count we just talked about, over 1,000, and which is an easy proportion to get. 0.82, or if you want to talk about it being 82%, it's fine to write it with a percent sign. And what we just found was a probability. Now your textbook uses capital letters A, B, and C to represent generic events. I like to, in any problem, if I have to write it out to some extent, use the problem itself. So how about just the problem here being the probability of being satisfied? A little abbreviation there. That's the probability of the event we found. Just find out the total number, figure out all the different ways it can happen. Here there were 820 out of the 1,000. So there's our first probability, which should lead you to be able to answer part B pretty easily. Now I want the probability that a customer was not satisfied. So there's a couple ways you could do it. Right? You could do the same thing we did in A in terms of finding the count, or the fact that we already had the satisfaction rate, what would be the not satisfied rate? Just doing 1 minus or 100% minus, doing a complement idea. The probability of not satisfied would be 1 minus the probability that they are satisfied. So I could simply do 1 minus the 0.82 for 18%. That would be one approach. If you've already got and did the trouble of counting up the ways of it happening, and you want now the ways that it wouldn't happen, the complement rule. We just worked out one of the rules. It's called the complement rule. You could have also just found the probability of not satisfied directly here, because that would not be too hard. Either would be fine. And I would not need to see all this work on a problem that's this simple on an exam. But if it were that the numbers were not as easy to divide, I'd like to see your denominator and kind of see what your numbers are going to work out from. But again, I'm just writing these things out so you can see its relation to these rules that are going to be in your book and see that we're doing those rules. One thing that does help, this complement rule. Sometimes the probability of the thing that you want is really complicated to work out. There's so many different ways to figure out that proportion. If you think about the complement, what's not in that event, that might be very simple. Very easy to count up and then get the other one by subtraction. And we'll do that quite a bit in some of the examples we do later today. All right, how about part C? Now we're looking at a combination of events. I want the probability that if I select a person at random, they are satisfied and received it on time. So again, I need the proportion. I think I asked you to talk about that number earlier. I need the number of people who were satisfied and on time, and that would be how many? That 800 right there. There were 800 people that had both of those outcomes. They were satisfied and received it on time. So 800 out of 1,000 is 0.8, or 80%. And you just found the probability of an intersection. The word and means intersection, or both, satisfied and on time. And finding the probability of A and B, the intersection, here was very easy. Whenever it's a two-way table of counts, which is one way to display things to work out probabilities, very easy to find the probability of an A and B. There's a formula that we'll look at on the next page, and it's very complicated at the top there. We didn't have to do that approach at all, because we could simply look at and find all the intersections in the middle of the table. All of those inside the table cells are indeed the ands. So they are already right here for us. We will have a rule that helps us find the probability of A and B when things are independent of each other. That helps us out a bit. But here it was straightforward. Find the intersection and divide by the total. Now that's different than part D. This is the word and in between, the intersection. Part D is asking to find the chance that they are either satisfied or received it on time. So I want everybody that was satisfied, I want everybody that received it on time, put them all together. That's what I want to do. So one approach is to first find the probability of being satisfied. So let's do the satisfied first. Satisfied was what? All 820. And then let's add everybody who was receiving it on time. So everybody who received it on time is 880. Now is that the right adding up here that I need to do? I've included those 800 people in that intersection twice. So when you do the approach of saying I want either one of these, you take everybody here and you add to them everybody here. There could have been quite a few in that overlap. So you have to subtract that off once. We would have to subtract off the 800 to get the right count, truly out of 1,000. It would be the 800, the 80, and the 20 really added up for a total of what? 900. We found the probability of or, satisfied or received on time. We just had to be careful not to count people twice when we started to work out our totals. From the table, it's easy to not count twice and just to add up the ones that are needed. If we had told you 820 people were satisfied, 880 were receiving it on time, and 800 were in both, you'd have to add those up and subtract and work that out. The rule says if you want to find the probability of an OR between any two events, you take the first one, which we did, we took the 800, you add to it the chance of the other one, and then don't forget to subtract off the and or intersection, because when you did this, you've added them in twice if there's anybody there. So the rule says to subtract off the satisfied and on time. It has the probability of A plus that for B, subtract the probability of the intersection or the and, which isn't too hard to find from our table. So the rule is long. We would go to our table and pull off the right counts, and I really wouldn't need to see any kind of rule written out. But sometimes we don't have the table layout. We just have certain counts for us, so we could work through some probabilities, and that's one of the results for an OR. OR is union, and is intersection. OR means at least one of those two things happens, either satisfied or on time, or maybe both. And the and means they both have to occur. All right. E and F are similar. They start with a keyword, that keyword being given. So what do we want here? Given a customer did receive their items on time, so I'm looking at that group. I'd like to know what's the chance that they were satisfied. So I'm not looking at all 1,000 customers anymore. I'm looking at only those that received it on time. I want the probability of being satisfied, but not for the entire group, but only this group right here. Given received it on time means focus on the first column, on that group. Pretend like that's your population now, and you don't have 1,000 customers, you have 880, and now I want the satisfaction rate or proportion. So what would that be? How many were satisfied? 800 out of 880. And what is that fraction? About 90 some? About 91%, I believe. 909. And you just found a conditional probability. Conditional probabilities are calculated quite often. We're constantly updating chances of things happening based on new information coming in. Now, knowing that the person had received it on time, how likely is it that they're satisfied? The notation for a conditional probability has a big vertical line in the middle between these two events. The probability that you were wanting, the event you wanted to know the chance of, which is being satisfied, comes first. I want to know how likely is it that they're satisfied, the probability of satisfied, given, conditional on, that they received it on time. That's how you write out a conditional probability. I want the satisfaction rate among this group. Given they received it on time, how likely is it that they were satisfied? And you just found the right conditional probability. Now there's quite a formula behind that. The formula behind it says take the probability of the and, the intersection, in the numerator. And it says always divide by the given event. That always goes on your bottom as your new base. Well, we really did that. The on-time rate, the on-time total was 880 out of 1,000. And the intersection that we found in the earlier part, the and between those two events, was this 800 out of 1,000. So what happens to those 1,000s? They cancel right out. So we did do the conditional rate. You just have to visually focus on one column or one row, whichever you're conditioning on, and work out the rate out of that. This is the formula behind it. You take the and in the numerator, conditional on the denominator, and that works every time. So let's have you work out part F. It's the other rate for satisfaction, given you picked the other kind of customer. So at least work out the right fraction that we would work out here. So the short but correct answer here would be what? What's in the bottom? What's the count? 120? 120 people altogether were not receiving it on time. And how many were satisfied out of that group? Just 20. This would be completely correct. I would not take off any points. Obviously, it's nice to convert it to a decimal form to compare things easier. And that decimal form would be a much lower rate of about what here? 16, 17%? And although I don't need it for any specific credit, it is sometimes helpful to know what you did find. Because one of our definitions we're going to look at makes us compare a couple probabilities, and we need to know what those probabilities are that we work through. So there's that line for the conditioning part. What goes in each spot? Probability of satisfied given they received it not on time, given they didn't receive it on time. So the satisfied still up front, and given it was not on time. And that's the event you found. All right, so what was the satisfaction rate overall in Part A? 82% were satisfied. And if they didn't receive it on time, it dropped down to about 17%. If they had received the items on time, that satisfaction rate went up to about 91%. It seemed to be changed or influenced by whether they had received it on time or not. And that'll play a role. So you just worked out a number of probabilities here with me. Many of the rules that you actually did use, but not quite in the long formula way, are on the top of the next page. Here's how the textbook writes out the complement rule. Well, we did do that in Part B. Here's the generic rule for the or between two probabilities, the union. It's called the addition rule, because you add the two parts up and don't forget to subtract off the overlapping piece. We didn't really use this multiplication rule. This is the rule that relates how to find the probability of A and B for any two events A and B. It actually comes from this more useful one on the bottom, the conditional probability rule. They are directly related, just solving them for the other piece that's set aside on the left. The probability of A given B, probability of satisfied given on time, you found the intersection on the top, and the given event goes on the bottom. That's the general rule for updating probabilities. The multiplication rule is just a rearrangement of that, which really doesn't help us because it was easier to find the and just directly from the table, just how many were in the overlap. If you've got the overlap, don't have to work out a formula for it. So again, I don't need to see A's and B's. I don't need to see the long formulas written out. But those structure and how they do relate are on your yellow card, so you don't have to memorize them if you did want to refer back to them. And there's also a few other definitions that are on there that will be helpful for us. I encourage you to read through the remaining part of this page just because it kind of takes you through the reasoning again of where these probability rules come from using a Venn diagram approach. So read them through on your own. But we're going to go back to a couple definitions on page 36 and apply them to our customer example. So we calculated some basic probabilities, some intersections, some unions or ors, some conditional probabilities. Now there's a couple ways that events are related. One is called, are they mutually exclusive or not? And another is whether they're independent of each other or not. And they are different definitions. The first one is mutually exclusive. Two events are said to be disjoint, that's another word, or mutually exclusive if they don't have any outcomes in common. If their intersection is completely empty, they don't overlap. I can see it in a Venn diagram. You can picture these events. I don't even need to have probabilities written in there. As long as those two sets don't overlap and have any outcomes, then they're disjoint. Obviously, if they are disjoint, then the probability of any intersection, probability of having anyone in that overlap is 0, which makes some of those formulas simplify too, that we just saw. So disjoint is a property about the sets themselves. Is there anybody in the overlap? Or is it a 0 there? Because there's nobody that can have both. Nothing about the probabilities has to be checked, although I know that the probability then of that intersection would be 0 if they are disjoint. So that's one definition. It's about the sets, and you've got a little summary of the rules that simplify there. The other one that's a little bit harder to see, because you can't picture it in a Venn diagram, is this thing called independence. Now, we already talked about independence a little bit in a random sample idea. We want the probability of seeing something occur not influence the chance of other things happening later on for other people. It can be formed in this probability definition here, too. Two events are said to be independent if knowing that one has occurred does not change the chance of the other occurring. No influence. It's written in notation this way. What's the probability of A happening if you know B occurred? Well, if they're independent, having that knowledge that B occurred makes no difference. It's just the chance of A happening in general. Or flip them around, because if A and B are independent, this result would hold too. The conditional becomes the non-conditional, or the basic event probability. Knowing that the outcome happened doesn't change. If the chance of favoring a certain outcome for males is the same as the chance of favoring a certain outcome for females, well then gender doesn't matter. You could put them all together and get that same overall rate of favoring that outcome. And then the rule for multiplication simplifies if they're independent. Multiplication rule before was much more complicated. It had an A given B followed by the B. Well, they end up being just the plain multiplying of those two probabilities if they're independent. I remember this rule. I don't know why I keep remembering this from my days of coming up with my little script sheets of probability results when I had to study for my exams. I call that the AIM rule. If it's an and they're independent, you multiply the probabilities. And that does extend to any number of events. Very useful for finding some complex probabilities when you know you have independence, when you know you took a random sample, and you can have that independence. So let's try checking these definitions out. Our last two questions on our shopping online example ask those two basic questions about two events. So I picked two of the outcomes, two of the events here, satisfied and receiving it on time, and ask if they're mutually exclusive or disjoint. And then part H is asking if they're independent. So mutually exclusive comes first, or disjoint. That's the set property. That's asking, are there any people in the overlap? Being satisfied and receiving it on time. Were there any customers that were both satisfied and received it on time in the overlap? Yeah. How many? How many customers were satisfied and received it on time? 800. There's not a 0 there. There's 800 people there. That's not an empty set. There are 800 people. So are they disjoint? No, they're not disjoint. They're not mutually exclusive. There were 800 customers. In the overlap. Both satisfied and received it on time. In order for two events here to be disjoint, their intersection has to have a 0 count there. I have 800, I have 20, 80, 100. There's no zeros in my table in the middle. So I can't take any event from one row and any event from the column and say they're disjoint, because there's always some numbers there. Can you give me, out of my different events here, two that are disjoint, though? Either you were satisfied or not satisfied. Is there anybody that was both satisfied and not satisfied? You set up your rows or you set up your columns to be disjoint possibilities. So if I asked you, give me two events that are disjoint, you couldn't combine any satisfied type of outcome with the on time, because there's always people in those overlaps, but take any two from the same columns or same rows, and you've got, by definition, these disjoint outcomes. So satisfied and not satisfied are disjoint, and on time versus not on time are disjoint. If you have to come up with an example of disjoint, take any event you want and take its complement. And those are by definition not going to be overlapping. All right, but here these two events are not mutually exclusive. They are not disjoint. Now that does not necessarily influence what your answer to the next question is. The next question is about independence of these two events. And for that we have to check probabilities. Are they independent? Statistically independent. Now the definition, there are three possibilities. I'm going to write them on the side here so we just know what we could reference. You've got them on the previous page. You could say the probability of A given B is just the probability of A. That's one definition. Or the other one could switch the two around, which I won't be redundant to write that out. But then there was that AIM rule. Probability of A and B should be what? They're and independent, you can multiply. So these are two definitions of independence that I could look at. They're both on your yellow card, so if you can't remember that definition, they're there. The idea is, if you know that one of those events happened, does it influence the chance of the other occurring? And didn't we just work through that if you knew they didn't receive the item on time or they did, that it made a difference to their satisfaction rate? Right? When they received it on time, what was their satisfaction rate then? That was at 91% or so. But when they worked out just the chance of being satisfied, that was only about 82%. You're asked, does the probability of being satisfied depend on the other event happening or not? The probability of satisfied, given you know it was on time, is that equal to just the overall satisfaction rate? If those two probabilities are equal, then those events of satisfied and getting it on time are independent statistically. But what did we find? The satisfaction rate on the left, that conditional rate was one of the ones we worked out. That was the 800 out of 880, or about 91%, whereas the overall satisfaction rate was about 82%. They're not the same. Knowing they received it on time did change the probability that the customer would be satisfied. Therefore, these two events are not independent, they are related. They're associated, they're dependent. Probability have to be checked. They're not independent. Now, you could have checked the other rule too, but that would have been a little bit more work to do that, because we didn't already have those probabilities all worked out in the earlier parts. If you're working through a probability question and one of them towards the end is, are these things independent? You might just have to compare a couple probabilities you've already found using the definition of independence to see whether that statement would hold or not. You could have equivalently used the AIM rule. You would have had to take the probability of satisfied and on time and see if that ends up being equal to the product of the two probabilities. Satisfied times the probability of being on time. Right very well at the end there. And we did find the and. We found the satisfaction rate, but we never really looked at the chance of being on time specifically. But if you worked those out and did the multiplying again, they would not be equal. So you don't have to check all equivalent definitions. One applies the other. But depending on what you're working with, you might be able to check it more readily. Being mutually exclusive, being disjoint does not mean they are independent. Because independence is a probability statement, and being disjoint is simply based on the sets themselves, and not a relationship between probabilities. In fact, here we have events that were not disjoint, but they were not independent. And you can have not disjoint with independence too. All right, statistically independent. The probability that the first person says yes, given you know that the second person you surveyed said yes, well, that doesn't matter. They're independent outcomes. We have independence when we take a true random sample. All right, let's try it out with one more example. Oh, I've got my pictures of the day. Here's what we did yesterday. Did a little skiing just to get our ski legs back and see if we're ready to go out for further trips. So my daughter's very colorful. She has red and pink and brown and blue, and she likes to be eclectic, she says, dressing. Yeah. All right. Let's try another example, a couple of them in a row here. This one is with a Venn diagram. Venn diagram's already completed for us and ask us to work out probability. So another way to give you information is to provide a Venn diagram, or you might be able to take what's given in the problem and put it into a Venn diagram. You could have converted this to a two-way table also of having diabetes or not, living below the poverty level or not. Could have worked it out that way too. So what does it say in the background? 10% of the people have diabetes, 30% live below the poverty level, 5% have both. The both means you're talking about the and. So I know you can probably work out these probabilities pretty straightforward, but do you see where the numbers come from in the diagram first? I know that there's an overlap because there's a both. I have a diabetes and a below poverty level. The 5% in the middle is that both. 0.05 is the probability. Why did I not put in this spot right here 10%? Because the diabetes part should be 10%. The total diabetic rate for the entire should be 10%, 10%. And so I've got 5% in each of those, so they add up to 10%. So I make sure that my total for that circle is 10% in all. Likewise, the total for the below poverty level circle should be a total of 30%, and I do have that there. And then if 25, 30, 35% is in the circles, 65% is left over to make sure it's 100% in all. So with a Venn diagram, any of these probabilities are easy to find. Don't have to really write out the full formula. If we know the diabetic rate was 10%, what's the answer to part A? Chance that they're not diabetic? I could write that down. I could type that up in my homework online, 90% or 0.90. And I don't really have to show much work behind that because I can do that in my head. Probability of not diabetic. The answer is 0.9, 0.90 or 90%. What we did is we found not diabetic using the complement rule. Doing 1 minus the 0.10 to get our 90%. Now that's easy to subtract in my head, so I didn't have to work that out in detail. But we were using the complement rule. How about part B? This is looking for picking a person and they're either diabetic or they live below the poverty level. Or means put them all together. So if I want the probability of diabetic or living below poverty level, I would take the diabetic group first and then add to it the probability of being in the other group, because I want a combination of both. But what do I have to subtract off then? Any intersection that I might have double counted. Diabetic and below the poverty level. Diabetic was 10%. Below the poverty level was a total of 30%. But there were 5% in both. Don't want to include them twice. So I get the 40 minus 5, we're back to 35%. And do you see that back in your circle as just this part right here? The 25, 5, and 5, 35%. The or is shading all the parts that make up those different events, putting them all together. And if you got the individual little pieces, you could just add them up too. What's the key word in part C? Given we know that they live below the poverty level, now how likely is it that they are diabetic? Can we write out the right probability with that line? What's the probability I want to find? The event is find how likely they are diabetic, given we know that they live below the poverty level. Now, whenever you have a given probability, a conditional probability, think of the given event and look at only that group. You don't want to look at all 100%. You want to look at only those that are living below the poverty level. So focus on this circle right here. That's your new sample space. That's your new population. And what percent are in there? 30%. So out of the 30% that live below the poverty level, give me the right rate for counting up those that are diabetic. So now I want to look at the diabetic part of that new population that I'm focusing on. The diabetic part would be just that part right there. That intersection, which is how much? What percent? 5. So it's 5 out of 30. 5% out of 30%. We took the and on the top, the intersection, which is 5%, and divide always by the given. That's your new base. So it's not out of 100%, but out of the 30% you started with. It's about 16, 17%. There's again another conditional probability. Knowing the way these end up structuring, if you can just put the denominator number and put the right numerator on top, then that's really all the work I need to see. But that is the probability we just found. Probability of seeing diabetic happening among the below poverty level group. That's the 5% out of the 30%. All right, so with that probability worked out, and knowing that the diabetic rate initially was what? What was the overall diabetic rate for the entire population? 10%. And if you know they live below the poverty level, it's now up to 17%. So what do we fill in here? I'm just recapping. Diabetic rate was 10%. Our conditional from part C. Looking at D at the bottom of that page, what do you circle? If we knew that they lived below the poverty level, did it change the chance of being diabetic? Yeah, it went from 10% to 16%. It did change. It did affect the probability that they're diabetic. Since it does influence or change that probability, then what do we know about those two events of diabetic and below poverty level? They are not independent. They are related. Knowing one occurred does change the probability of the other happening. That's the basic definition. So 2 examples of where things are related, which happens quite a bit actually. And interesting to see if that relationship is significant or not. One of our last full numeric examples is here. Question first. Yep. If it ended up being that when you took out of your 30% a right count or number, and that ended up being back to 10% again, then you would say there really is no difference. Even though there is an overlap, the rate within that one section is the same as the rate overall. So whenever the probabilities are equal, then knowing the event happened didn't change the chance. You're looking at a smaller subset, but the rate within it is the same. So if the 2 probabilities have been the same, they are independent. When the 2 probabilities differ, then your probability of seeing that outcome changed based on knowing some information about that person you selected. Now, sometimes in data, those numbers are likely not to be the same, but they're close. And when they're really close, you might say, well, there's evidence of possible independence there. And we have a test for that later that we'll be doing. But for now, this is the definition, and you'll be asked to apply that definition. There are times when you're going to be asked, are these 2 events independent? We just had that twice now. One for the customers, and now for the diabetic and below poverty level example. There are other times when you have been told you have independence, and you can use it. And that's our next example here. So very simple background. About 1/3 of all adults have a certain type of blood. And we're going to pick 3 people, 3 adults from this population at random. So if I say we have a random sample, what are the 3 letters we can think about that tell us some clue about those observations? From chapter 4, if we have a random sample, I want you to think of IID. Random sample means IID. Those observations are IID. The first I is what? They are independent. They are independent observations. The probability the second person has type O positive blood, it does not influence whether the first person does or not, or any other person in the list. They are independent. The second part of that IID is identically distributed. That just means they all came from the same population with that same model, that 1/3 have type O positive blood. That the population they came from was the same and had the same distribution or model, identically distributed. That 1/3 applies to everyone in that population. So the chance that the first person has type O positive blood is 1/3. And what's the chance that the next person coming out of there will be type O positive blood? 1/3. The model or distribution that tells you how blood type is distributed is the same for everybody in that population, identically distributed. So that allows us to answer all these probability questions. But the key is whenever you see you have a random sample, you have independence of those observations. And you can use the AIM rule. You can use that conditional definition of independence. So let's take a look. First question, what's the chance that the first person has type O positive blood? We just talked that through. 1/3. That's the probability that the first has type O positive blood. So there's my event. I'm going to randomly select 3 people. The chance that the first has type O positive is 1/3. The chance that the second does, 1/3. Each of these probabilities for each individual outcome are all 1/3 because they're identically distributed. They all came from the population that has 1/3 with type O positive blood. All right, I didn't ask the third one, but if the third was selected randomly, they also have a 1/3 chance of having type O positive blood. What do I ask in that next question? Now, an event about all 3. What's the probability that all 3 will have type O positive blood? So what does that mean? The first person has type O positive blood, and the second person does, and the third person does, right? In order for all 3 to have that type of blood, they all do. This one does, and this one does, and that one does. What do we do when we have ands and they're independent outcomes? You can multiply. The probability that all 3 do, I'm writing it out long ways. You would just have to multiply 1/3 times itself 3 times. But that the first has type O positive blood, and the second does, and the third. When they're ands and they're independent, you can multiply their probabilities. And each of those probabilities is 1/3, so it's 1/3 times 1/3, or raise it to the 3rd power. And that probability, 0.037, I believe, if decimal form is correct. Fairly small. Only about 1/3 do. The chance of seeing all 3 with type O positive blood could happen about 4% of the time. Now, what's the probability that none of them will have type O positive blood? So the first one doesn't, and the second one doesn't, and the third one doesn't. What do you do now? So what's the chance that the first person doesn't have type O positive? 2/3. And that's the chance for every other person. And what do you do with those 2/3? You multiply, accumulate them up and multiply again. The chance that the first one doesn't and the second one doesn't is 2/3 for each of those. So 2/3 to the 3rd. And that's a little more likely, 0.296. That's the probability that none have type O positive blood. The first one doesn't, and the second one doesn't. And I'm not going to write the whole thing out again. But you get the idea. Could you work out the probability the first one does, and then the other 2 don't? What would that be? 1/3 times 2/3 times 2/3. You could do any combination like that for those 3 outcomes and just multiply the probabilities because they are independent. Good. And there's lots of combinations that could happen there. Our question here is the probability that you would get at least one having type O positive blood. So there's 3 people, and you want the chance that at least one has type O positive. So that means the first one could, but maybe the other 2 don't. And that's what we just worked out, right? 1/3, 2/3, 2/3. But then you could also have, it's the second person that does, and the first and the third person don't. But that, you just multiply that out too. Or it could be that the first 2 have type O positive and the third one doesn't. There's lots of possibilities here, aren't there? To have one person doing it, or 2 in a couple different ways, or all 3. And you could find all those and add them all up to find the total probability of this event. But a key of at least one, seeing that phrase, should trigger, should I do the complement rule instead? Because at least one is 1 or more. There could be a lot of possibilities for 1 or more. And to try to enumerate them all and not miss one and make sure you add them all up correctly, that can be a lot of work. The complement of at least one is very easy. Probability of at least one having type O positive blood is the complement that none. And then we just find the probability of none. We just subtract. The probability of at least one. At least one has type O positive blood is 1 minus the probability that none of them do. At least one is 1 or more. That's 1 or 2 or all 3. The only thing that's not there is the 0. None of them do. And the none was easy to find. We found that as 296 from the previous part. So this is 704. At least one out of many, even if that many is only 3 people, usually easier to find with the complement rule. At least 1 out of 2 is just the or between them. That's not too hard to find, straightforward. Complement rule is very helpful. We use complement rule. We used the idea of independence. And then it didn't say in the problem you have independent observations. It said you have a random sample. So keep that in mind. Random sample means you have independent observations. Good property of that random sampling. Couple notes to go through, and we get out a little early as usual. But please let me highlight those couple notes with you. I sort of lied a little bit. We really don't have true independence, but it's close enough. When you take a population and you take out that first person, haven't you changed the population? If there were 100 people in there, now there's only 99. And if half before were female, and that person you pulled out was a female, now there's 49 out of 99. But isn't that still about half? The idea is we sample from our population without putting the person back. I don't want to include the same person's opinion twice in my survey. But if you take the person out, then the population's changed. The model is changed. They're no longer identically distributed, truly. But when the population's huge relative to your sample size, then there's not really much of a difference between sampling with versus without. If there were 1 million people and half were female, taking that first person out and happening to know it's a female does not really change the probability of a female for that next draw. It's still about half. It's close enough. Sample with or without replacement. We sample without replacing, but those probability results, that idea of having independence and identically distributed, still hold, provided the population's large. And one of the rules is the population's 10 times bigger than your sample. And usually your populations are quite large. If they were small, you might be able to actually look at everyone in the population and do a census instead. So we usually don't have to worry about that, but that's a little side note. Here's probably the most important one of these notes, and that is I get students all the time, and this will come with practice, on trying to understand the difference between mutually exclusive and independence. They think that if they're disjoint, mutually exclusive, well, that means they're independent. They're not touching each other. That's actually wrong. If they're disjoint, they are going to be independent. Because independence is that probability statement. If they're disjoint or mutually exclusive, they're often going to be dependent in the following sense. If you had a population That was half males and half females. So the probability of a male is 0.5, probability of female 0.5, or probability of Democrat, Republican, whatever you want to work out that are two disjoint outcomes. Well, they are disjoint. Will they be independent? Independence says the probability of seeing one given it was another is supposed to be the probability of the first. What's the probability that I have a male that I pulled from the population when I know it was a female? 0. Right? Doesn't happen over the chance of being a male. What's the probability of Democrat given you know you picked a Republican? So when they're disjoint, when you're in one, you can't be in the other. That's the definition of being disjoint. There's not an overlap. So if they are disjoint, they are dependent, because if the probability of being in one given the other, that would be 0. You know you're in the other one if you're not in this first one. There's a direct relationship. If they're disjoint, they're dependent. This probability will not hold because the probability of seeing one outcome given the other occurred, well, if this one occurred, this one couldn't have because they're disjoint. You have to check the two definitions separately. Easy to check this one. You just go to your table, look at your counts, and see there's a 0 there. Not as easy to check the independence because it requires calculating some probabilities and seeing if that relationship holds. But maybe you've already calculated some of those probabilities along the way, so it's not too bad. Independence is a probability property. Disjoint is all about the sets themselves. Don't get those two definitions mixed up, is my main message. There's that full list of rules. It's on your yellow card. What I want to point out, exam 1. I ask you if something's independent, and you start working through the check, and you write out the definition wrong, but it's right there. And it's right up there. I can't reach. The definitions are there for independent events. So use those definitions if you need to when you work through those questions. I believe that is all for today.